What if the edge of our solar system is not a quiet boundary, but a place where something is already reaching back toward us? Far beyond the orbit of Pluto, past the fading influence of sunlight, drifting in a region where even time feels stretched thin. A spacecraft the size of a small car continues its silent journey. It has been travelling for nearly half a century. It carries no crew. It was never meant to return. And yet even now it is still speaking to us. Voyager 1 is more than just a machine. It is the most distant human object ever created. A fragile messenger crossing into a region humanity had never touched before. According to NASA, it officially entered interstellar space in 2012, leaving behind the protective bubble of our sun known as the heliosphere. For decades, scientists believed they understood what that boundary would look like. A smooth transition, a gradual fading of solar influence, a quiet crossing into the vast emptiness between stars. But that is not what Voyager found. Instead, it began detecting something strange. Not a single event, not a glitch, but a pattern. Subtle at first, easy to dismiss, then possible to ignore. Signals began to change. Not the radio signals sent from Earth. Those remained steady, travelling across billions of kilometres with astonishing precision. No, the change was in what Voyager itself was measuring. The environment around it was behaving in ways that did not match predictions. Plasma waves appeared where there should have been near silence. Magnetic fields shifted in unexpected orientations. Particle densities rose and fell as if something unseen was passing through the region. At first, scientists thought these were local effects. Perhaps turbulence caused by the sun's influence extending farther than expected. But the deeper Voyager travelled, the stranger the data became. It was as if the spacecraft had crossed into a place that was not empty at all. Imagine drifting into a dark ocean expecting calm waters only to feel a current pulling, gently but persistently against you. You cannot see what is causing it. You cannot map it clearly, but you can feel its presence in every measurement. That is what Voyager is experiencing. And here is where the mystery begins to deepen. Because according to long-standing models, the heliosphere acts like a shield, a vast bubble created by the solar wind pushing outward against the interstellar medium. This bubble was thought to be relatively stable, shaped by the sun's energy and the surrounding galactic environment. But Voyager's data suggests that something outside this bubble is not passive. It is interacting. Not violently, not dramatically, but consistently. A study published in journals like the Astrophysical Journal has discussed unusual plasma oscillations detected by the Voyager. These oscillations indicate that the density of interstellar space near our solar system is higher than expected. That alone is surprising. But more intriguing is how these waves behave. They arrive in bursts. They change over time. They carry signatures that imply movement and structure. In other words, the space beyond our solar system is not uniform. It is dynamic, and something within it is influencing the very edge of our sun's domain. You might think of space as empty, a vacuum, a silent void. But in reality, it is more like a thin, invisible atmosphere made of charged particles, magnetic fields, and faint traces of gas and dust. And our solar system is moving through it. Not slowly either. The Sun, along with all its planets, is orbiting the centre of the Milky Way galaxy at roughly 220 kilometers per second. That means we are constantly travelling through different regions of interstellar space, each with its own properties. So what happens when we enter a region that is different from what we expected? That is the question Voyager is beginning to answer. Because the data it sends back does not just describe where it is, it reveals what we are moving into. And some scientists are beginning to suspect that the changes Voyager is detecting are not random fluctuations. They may be the early signs of a transition into a new interstellar environment, a region with the higher density, stronger magnetic fields, and possibly structures we do not yet fully understand. According to NASA researchers analysing Voyager's plasma wave instrument, the increase in electron density suggests that the spacecraft is travelling through regions where interstellar material is being compressed. Compressed by what? That is where the mystery deepens. One possibility is that we are encountering a boundary between different interstellar clouds, vast regions of gas that exist between stars, each with its own temperature density and magnetic characteristics. Another possibility is more unsettling, that the heliosphere itself is being shaped or even disturbed by something external that we have not fully mapped. Because if the boundary of our solar system is not stable, then everything inside it exists within a constantly changing environment, and Voyager is the first witness, the first observer, the first to feel the subtle pull of whatever lies beyond. But here is the most intriguing part. The signals are not random noise. They form patterns, repeating structures and plasma waves, consistent shifts in magnetic alignment, variations that occur over timescales that suggest something larger is influencing them. Something with structure, something with motion, something that is not just drifting aimlessly through space. And yet we cannot see it. Even our most powerful telescopes, like the James Webb Space Telescope, cannot see and directly image these regions in detail. They can observe distant galaxies, detect the atmospheres of exoplanets, and peer back toward the early universe. But the immediate environment just outside our solar system remains largely invisible. We are in a sense blind at the edge of our own cosmic neighborhood, and Voyager is our only probe in that darkness. Every piece of data it sends takes over 22 hours to reach Earth, a faint whisper crossing unimaginable distance. And when it arrives, scientists listen carefully, searching for meaning in the noise, because somewhere in that data is the answer to a question we did not even know to ask. What is waiting outside our solar system? Is it just a denser region of interstellar gas? Is it a shifting magnetic landscape shaped by the galaxy itself? Or is it something more structured, more organized, more complex than we have ever encountered before? Right now we do not know, but we are beginning to see hints. Hints that the boundary we thought was quiet is anything but. Hints that space beyond our sun is not empty but active. Hints that our solar system may be moving into a region that will change how we understand our place in the galaxy. And all of it begins with a small spacecraft drifting silently in the dark, sending back signals that refuse to behave the way we expected. Signals that suggest something is out there, not watching, not waiting in the way stories might imagine, but existing, moving, interacting, and slowly, almost imperceptibly making its presence known. And if that is true, then the next question becomes unavoidable. What exactly did we think the edge of our solar system looked like in the first place? For most of modern astronomy, the edge of our solar system was never imagined as a place of mystery. It was a boundary, yes, but a predictable one. A natural consequence of the sun's influence fading into the background of the galaxy. If you could travel outward from Earth, past Mars, beyond Jupiter, crossing the icy orbits of Uranus and Neptune, and finally slipping past the distant Kuiper belt, you would eventually leave behind the region dominated by the sun's solar wind. That invisible stream of charged particles constantly flowing outward defines a vast bubble around our star. This bubble is known as the heliosphere. According to NASA, the heliosphere acts as a protective shield, deflecting a significant portion of high-energy cosmic rays that originate from outside our solar system. Without it, Earth would be exposed to far more radiation, and the conditions for life might be very different. For decades, scientists believed they understood how this boundary behaved. The idea was simple. The solar wind expands outward in all directions like a balloon inflating in space. Eventually it encounters the interstellar medium, the thin mixture of gas plasma and magnetic fields that fills the galaxy. At that point, the outward pressure of the solar wind balances with the inward pressure of interstellar space. That balance creates a boundary. First, there is the termination shock, where the solar wind slows down abruptly as it begins to feel resistance from the interstellar medium. Then comes the helioskeith, a turbulent region where solar particles are compressed and heated. And finally, the heliopause, the outermost boundary where the sun's influence effectively ends and interstellar space begins. Beyond that, the expectation was clear: calm, stable, uniform. Interstellar space was often described as nearly empty, with only a few atoms per cubic centimetre. A cold, quiet void stretching between the stars. Once Voyager crossed the heliopause, scientists expected its instruments to detect a relatively steady environment with only minor variations. In other words, nothing dramatic. Nothing dynamic. Certainly nothing that would suggest ongoing interaction at a large scale. This model was not just speculation. It was built on decades of observations, theoretical physics, and indirect measurements. Missions like Ulysses and Ibex provided valuable data about the shape and behavior of the heliosphere. They revealed that it was not perfectly spherical, but more like a comet with a rounded front and a trailing tail, shaped by the sun's motion through the galaxy. Still, the fundamental assumption remained intact. The boundary was passive. The heliosphere pushed outward, the interstellar medium pushed back, and the result was a relatively stable interface between two regions. But there was always one limitation. All of this understanding came from indirect observation. Before Voyager 1, no human-made object had ever crossed that boundary. Everything we thought we knew was based on models and remote sensing. We were in a sense trying to understand the shoreline of an ocean we had never actually touched. And that leaves room for error. Because models, no matter how sophisticated, rely on assumptions. They simplify complex systems into equations that can be solved. They average out variations. They ignore small-scale structures that might not seem significant at first. But space is not obligated to behave simply. As Voyager approached the heliopause, scientists were eager to confirm their predictions. They expected to see a clear transition, a drop in solar particles, a rise in cosmic rays, a shift in magnetic field orientation as the spacecraft entered the domain of this galaxy. And to some extent, that is exactly what happened. According to NASA, Voyager detected a sharp increase in galactic cosmic rays, indicating that it had moved beyond the protective influence of the heliosphere. At the same time, the intensity of solar particles dropped significantly. These were strong indicators that it had crossed into interstellar space. But something did not match expectations. The magnetic field did not change direction as dramatically as predicted. Instead of a clean shift, the field lines appeared to remain aligned in a way that suggested a more complex interaction between solar and interstellar magnetic forces. It was as if the boundary between these two regions was not a sharp dividing line but a tangled interface, like two currents meeting in an ocean, mixing and folding into each other. This was the first hint that the heliopause might not be as simple as we thought. And then there were the plasma measurements. Before Voyager crossed the boundary, scientists expected the plasma density outside the heliosphere to be slightly higher than inside but still relatively uniform. Instead, the spacecraft began detecting fluctuations, not just random noise but structured variations. Plasma waves that rose and fell in intensity, signals that suggested compression, changes that implied motion. A study published in journals such as Nature has discussed how these plasma oscillations can be used to measure the density of interstellar space. By analyzing the frequency of these waves, scientists can infer how many charged particles are present in a given region. What they found was surprising. The density was higher than expected, and it was not constant. It varied over time. This raised an uncomfortable possibility. What if the region just outside our solar system is not uniform at all? What if it is structured, dynamic, and constantly changing? To understand why this matters, imagine standing at the edge of a forest looking out into what you believe is an open field. You expect to see flat land stretching into the distance. But as you step forward, you realize the field is filled with shifting tall grass, uneven terrain, and hidden currents of wind that move in patterns you cannot immediately predict. The environment is not what you thought, and that changes everything about how you move through it. For the solar system, this realization has profound implications. Because the heliosphere is not just a boundary, it is a shield. It protects everything inside it from a significant portion of cosmic radiation. If that shield is interacting with a dynamic external environment, then its shape, strength, and effectiveness may change over time. And if that happens, the conditions within our solar system could also change. Subtly, gradually, but significantly over long time scales. This is why the data from Voyager is so important. It's not just telling us where the boundary is. It is revealing what the boundary is made of, and more importantly, how it behaves. Because if the heliopause is not a simple static surface, then our entire understanding of the solar system's interaction with the galaxy needs to be revised. And that brings us to a deeper question. If the boundary is complex, if it is shaped by forces we do not fully understand, then what is shaping those forces? What is out there beyond the reach of the sun, influencing the very edge of our cosmic home? To answer that, we need to step back and understand the bubble itself, how it forms, how it moves, and why it might be far more fragile than we ever imagined. To understand what Voyager is encountering, you first have to picture something almost impossible to see. A bubble. Not a perfect sphere, not smooth, not still. A vast, constantly shifting envelope of energy and particles inflated by the sun itself, stretching billions of kilometers in every direction. This is the heliosphere. It begins at the surface of the sun, where intense heat and magnetic activity generate a continuous outflow of charged particles known as the solar wind. These particles stream outward at speeds of hundreds of kilometers per second, carrying with them the sun's magnetic field, extending its influence far beyond the visible light we see. According to NASA, the solar wind does not simply dissipate as it travels. It expands, fills space, and creates a region where the sun dominates the environment. Every planet in our solar system exists inside this bubble, moving through a sea of solar particles that are constantly interacting with planetary magnetic fields, atmospheres, and surfaces. But the solar wind is not uniform. It changes with the sun's activity. During periods of high solar activity known as solar maximum, the sun releases more energetic particles, stronger magnetic disturbances, and powerful eruptions called coronal mass ejections. During quieter periods, solar minimum, the wind weakens, becoming less dense and less turbulent. This means the heliosphere is always breathing, expanding slightly during active periods, contracting during quieter ones. Now imagine that bubble not floating in the empty space but moving through something, because our solar system is not stationary. It is traveling through the Milky Way, orbiting the galactic center at incredible speed. As it moves, it encounters the interstellar medium, a thin but complex mixture of gas dust and magnetic fields. So the heliosphere is not just expanding outward, it's also pushing against something coming from the outside. This creates a dynamic interaction. At the front of the heliosphere, where the solar system is moving forward through the galaxy, the solar wind meets resistance from interstellar particles. This causes the bubble to compress slightly, forming a rounded leading edge. At this back, the heliosphere stretches out into a long tail, carried by the flow of particles behind it. Data from missions like IBEX has helped map this structure. IBEX detected energetic neutral atoms that reveal how particles are interacting at the boundary. What scientists found was surprising even then. The heliosphere is not symmetrical. It is shaped by external forces, and those forces are not constant. This means the boundary is not fixed. It shifts. It changes shape depending on the environment around it. But for a long time, scientists assumed that while the shape might vary, the overall behavior was still relatively simple. The solar wind pushes outward, the interstellar medium pushes inward, and the boundary forms where those pressures balance. Think of it like a balloon being inflated underwater. The air inside pushes outward. The water outside pushes inward. The surface of the balloon forms where those forces meet. Now add motion. Imagine that balloon drifting through a current. The front is compressed. The back stretches. Small ripples form on the surface as the surrounding water flows past. That's a closer analogy to the heliosphere, but even that might be too simple, because the interstellar medium is not just a uniform flow. It contains regions of different density, temperature, and magnetic strength. Some areas are more like calm water, others are like turbulent currents, and occasionally there may be boundaries between these regions where conditions change abruptly. As the solar system moves through the galaxy, it passes through these regions, slowly over thousands to millions of years. And each region interacts with the heliosphere in a slightly different way. This is where things have become more complex. The sun's magnetic field carried by the solar wind twists into a spiral shape due to the rotation of the sun. This structure, known as the Parker spiral, extends throughout the heliosphere, influencing how particles move and interact. At the same time, the interstellar medium has its own magnetic field. When these two magnetic systems meet at the heliopause, they do not simply stop. They interact. They twist around each other. They reconnect. Magnetic reconnection is a process where magnetic field lines break and reconnect in new configurations, releasing energy and allowing particles to move across boundaries that would otherwise confine them. This process is well studied in solar physics and has been observed in Earth's magnetosphere. But at the scale of the heliosphere, it becomes much more complex, because now you are dealing with two vast magnetic systems interacting across a boundary that spans billions of kilometers, and this interaction is not smooth. It creates regions of turbulence, pockets of higher density, waves of plasma that move through the boundary like ripples through water. This is what Voyager is detecting, not a calm static edge, but a dynamic interface. An active region where forces from the Sun and the galaxy are constantly reshaping the boundary. And here is the key detail that changes everything. The heliosphere is not just shaped by what is inside it. It is shaped by what is outside it. For decades we focused on the Sun as the dominant force, and it is within the solar system. But at the boundary, the influence of the galaxy becomes equally important. If the interstellar medium changes even slightly, it can alter the shape and behavior of the heliosphere. If the density increases, the heliosphere may compress. If the magnetic field strengthens, it may distort the boundary. If the solar system enters a new region of space, the entire structure of the heliosphere could shift. And that's exactly what Voyager's data is hinting at, because the variations it is detecting are not random. They suggest that the environment outside the heliosphere is not uniform. It has structure. It has gradients. It may even have boundaries of its own. Imagine layers within the galaxy like invisible clouds, each with different properties. As the solar system moves through them, the heliosphere responds, adjusting its shape and behavior in response to external pressure. But if that is true, then the heliosphere is not a stable shield. It is a dynamic one, and that raises an important question. If the bubble around our solar system can change, then how much protection does it really provide? Because cosmic rays, high-energy particles from distant supernovae and other extreme events are constantly bombarding the heliosphere. The strength and structure of the heliosphere determines how many of those particles reach the inner solar system. If the heliosphere weakens, more cosmic radiation could penetrate. If it strengthens, less gets through. This is not just an abstract concept. It has real implications for Earth, for satellites, for astronauts, and for any future missions that venture beyond our planetary neighborhood. But right now, we are only beginning to understand how this system works. Because until Voyager, we had never measured it directly. And even now, we have only one data point, one spacecraft, one path through a vast and complex boundary. It's like trying to understand the entire coastline of a continent by walking along a single narrow trail. You learn something, but you do not see the full picture. And what Voyager is showing us along that trail is already challenging what we thought we knew. Because the bubble around our sun is not just expanding into empty space. It is pushing into something. Something that pushes back. Something that has its own structure, its own dynamics, its own influence. And as the solar system continues its journey through the galaxy, that interaction is changing. Slowly, subtly, but measurably. Which leads to an unsettling possibility. What if the region we are entering is different from the one we came from? What if the heliosphere is beginning to respond to a new environment? And if that is happening, then the next question becomes impossible to ignore. What exactly are the inconsistencies that first hinted something was wrong? At first, nothing seemed wrong. The models held, the equations balanced, the predictions aligned with decades of indirect observations. For years, everything about the outer solar system behaved the way scientists expected it to behave. And then slowly, almost imperceptibly, small inconsistencies began to appear. Not dramatic enough to cause alarm, not obvious enough to demand immediate explanation, but persistent. And in science, persistence is what turns curiosity into concern. Long before Voyager 1 crossed the heliopause, its instruments were already detecting subtle irregularities. The solar wind, which should have been steadily slowing as it approached the boundary, did not behave uniformly. Instead of a smooth deceleration, there were fluctuations, unexpected pauses, variations in speed, moments where the flow seemed to stall as if encountering resistance earlier than predicted. According to data analysed by scientists at NASA, the termination shock, the region where the solar wind is supposed to abruptly slow down, was not located where models had placed it. When Voyager 2 crossed this boundary in 2007, it found it closer to the Sun than expected. That alone was surprising. But what made it more puzzling was that Voyager 1 had encountered the termination shock at a different distance entirely. Two spacecraft travelling in different directions, crossing the same conceptual boundary, yet finding it in two different places. This suggested that the heliosphere was not just asymmetrical, it was distorted. Something was pressing on it unevenly. At the time, one explanation was that the interstellar magnetic field surrounding our solar system was stronger or oriented differently than previously thought. If the external magnetic pressure varied across regions, it could compress one side of the heliosphere more than the other. That made sense, but it was only the beginning. As Voyager 1 moved deeper into the Helios Heath, the region between the termination shock and the heliopause, scientists expected to see increasing turbulence. The solar wind, now slowed and compressed, should have formed a chaotic environment of swirling particles. And it did, but not in the way predicted. Instead of continuous turbulence, Voyager detected structured variations. Pockets where particle densities changed abruptly, regions where temperatures fluctuated more than expected, and most intriguingly, areas where the flow of particles seemed to reverse direction. It was as if currents were forming within the Helios Heath, moving in patterns that models had not anticipated. Imagine standing in a river that you expect to flow steadily downstream, but instead you feel eddies forming around your legs, currents pushing sideways, even brief moments where the water seems to pull back upstream. That is what Voyager was sensing. And then came one of the most confusing observations. As the spacecraft approached the heliopause, scientists expected a gradual transition in magnetic field orientation. Inside the heliosphere, the magnetic field is shaped by the Sun forming a spiral pattern. Outside, it should align with the interstellar magnetic field, which has a different direction. So crossing the heliopause should have produced a clear shift. But when Voyager 1 finally crossed that boundary in 2012, the magnetic field did not change as expected. It remained surprisingly aligned. According to studies published in journals such as Science, this alignment suggested that the boundary between the heliosphere and interstellar space was not a clean separation. Instead, it appeared to be a region where magnetic fields from both domains were interacting and blending. This was not just a minor discrepancy. It challenged one of the fundamental assumptions about the structure of the heliosphere. And then there were the plasma waves. Voyager 1 is not equipped with a dedicated plasma detector in the traditional sense. Instead, it measures plasma density indirectly through the detection of plasma oscillations. When disturbances pass through the plasma, they create waves at specific frequencies. By analysing these frequencies, scientists can estimate the density of the surrounding medium. What Voyager found was unexpected. The density of plasma just outside the heliosphere was higher than predicted. Not dramatically higher, but enough to raise questions. And more importantly, it was not constant. There were variations, repeating patterns, changes that occurred over time, suggesting that the spacecraft was moving through regions with different properties. This was not what a uniform interstellar medium should look like. It implied structure, layers, possibly even boundaries within interstellar space itself. And then came the bursts. At irregular intervals, Voyager detected sudden increases in plasma wave activity. These bursts were linked to shock waves travelling through interstellar space, often originating from solar events that had occurred months or even years earlier. When these shocks reached Voyager, they compressed the surrounding plasma, producing measurable oscillations. But the intensity of these bursts varied. Some were stronger than expected, some lasted longer. Some behaved in ways that suggested the medium they were travelling through was not uniform. It was as if the shock waves were moving through a landscape with varying density, amplifying or dampening depending on the region. This added another layer to the mystery, because now it was not just the steady-state environment that seemed unusual. Even transient events behaved differently. And then there was something even more subtle: cosmic rays. As Voyager moved beyond the heliosphere, scientists expected a steady increase in galactic cosmic rays, high-energy particles originating from outside the solar system. and that is exactly what they observed. But the increase was not sister smooth. There were fluctuations, small dips and rises, changes that did not correlate directly with solar activity. This suggested that the heliosphere's boundary was not a perfect shield and that its interaction with the interstellar medium was allowing cosmic rays to penetrate in complex ways. Taken individually, each of these observations might have been explained. A slight shift in the termination shock could be attributed to solar variability. Magnetic field alignment might be influenced by local conditions. Plasma density variations could result from measurement uncertainties. But together they painted a different picture. A picture of a boundary that was far more complex than anyone had anticipated. A boundary that was not static, not smooth, not predictable. Instead, it was dynamic, structured, influenced by forces both inside and outside the solar system. And perhaps most importantly, it was changing. This is what makes the Voyager data so compelling. It does not just show anomalies, it shows patterns. Patterns that suggest underlying processes we do not yet fully understand. And when patterns emerge in data from a region we have never explored before, it means one thing: we are missing something. Something about how the heliosphere interacts with the galaxy. Something about the nature of interstellar space. Something about the forces shaping the boundary of our cosmic home. And if we are missing something, then the question becomes unavoidable. What did Voyager actually find when it finally crossed into that unknown region? What did it see, measure, and send back that made scientists pause and reconsider everything they thought they knew? Because whatever it was enough to turn small inconsistencies into a much larger mystery. By the time Voyager 1 approached the edge of the heliosphere, it had already been travelling for more than 3 decades. Launched in 1977, it was never designed with this moment in mind. Its primary mission was to explore the outer planets, to capture images of Jupiter and Saturn, to send back data that would redefine our understanding of those distant worlds. And it did, but then it kept going. Long after its original objectives were complete, Voyager continued drifting outward, carried by momentum and guided only by the laws of physics. Its cameras were eventually turned off to conserve power. Many of its instruments went silent over the years, but a core set remained active, including those capable of measuring magnetic fields, energetic particles, and plasma waves. These instruments would become humanity's only direct connection to the edge of interstellar space. And what they found would not be what anyone expected. According to NASA, scientists had been anticipating the crossing of the heliopause for years. They were watching for specific signals, a drop in solar particles, a rise in cosmic rays, and a shift in the magnetic field that would indicate Voyager had entered a new domain. But the transition did not happen all at once. It was gradual, confusing, filled with moments that seemed to contradict each other. In 2012, Voyager 1 began detecting a sharp increase in galactic cosmic rays. At the same time, the intensity of particles originating from the Sun dropped dramatically. This was a strong indication that the spacecraft had moved beyond the heliosphere's protective influence. It was by most definitions in interstellar space. And yet something did not fit. The magnetic field direction remained nearly unchanged. Scientists expected a clear shift, a distinct boundary, where the Sun's magnetic influence would give way to that of the galaxy. Instead, the field lines appeared to remain aligned, as if the two regions were more connected than previously thought. This created immediate uncertainty. Had Voyager truly crossed the boundary, or was it still within some extended region of solar influence? For months, the scientific community debated this question. Papers were written, data was reanalyzed, models were adjusted. Eventually the consensus emerged. Voyager had crossed the heliopause, but the boundary itself was not what anyone had imagined. It was not a sharp edge. It was a region of interaction, a place where solar and interstellar forces blend together in complex ways. And then came the most striking discovery: plasma density. Voyager's plasma wave instrument detected oscillations that allowed scientists to estimate the density of the surrounding medium. The results showed that the density of plasma outside the heliosphere was significantly higher than inside. This was expected, but the magnitude of the increase was surprising, and more importantly, it was not uniform. According to research published in journals like Nature, the density appeared to vary over time, suggesting that Voyager was moving through regions with different properties. This was the first clear indication that interstellar space near our solar system is not homogeneous. It has structure, it has variation, it may even have boundaries of its own. Imagine leaving a calm lake and entering an ocean where currents shift, temperatures change, and unseen forces move beneath the surface. You're still in water, but the environment is fundamentally different. That is what Voyager experienced. And then there were the plasma waves themselves. These were not constant. They appeared in bursts. Some were triggered by shock waves travelling outward from the sun disturbances, caused by solar eruptions that had propagated across vast distances. When these shocks reached Voyager, they compressed the plasma around it, creating oscillations that could be measured. But the behaviour of these waves was unusual. Their intensity varied. Their frequency shifted. Their patterns suggested that the medium they were travelling through was not consistent. It was as if the shock waves were encountering regions of different density, amplifying in some areas and weakening in others. This added another layer to the mystery, because now it was not just the steady-state environment that was complex. Even transient events behaved in ways that hinted at underlying structure. And then came the magnetic field data. Voyager's magnetometer continued to record subtle changes in the orientation and strength of the magnetic field. While the overall direction remained aligned, there were fluctuations, small shifts, variations that suggested the presence of turbulence or localized structures. According to studies in the Astrophysical Journal, these fluctuations could be the result of interactions between the solar magnetic field and the interstellar magnetic field. But the exact nature of these interactions remains unclear, because we have never observed anything like this before. This is the first time a human-made object has entered this region, the first time we have had direct measurements, and with only one spacecraft interpreting the data becomes even more challenging, because we cannot compare, we cannot triangulate, we cannot map the region in 3 dimensions. We have a single path, a single stream of data, a single perspective on a vast and complex boundary. And yet even with that limitation, the message is clear. The edge of our solar system is not empty. It is not quiet. It is not simple. It is a place of interaction, a place where forces from the sun and the galaxy meet and influence each other. And perhaps most importantly, it is a place that is changing, because as Voyager continues to travel outward, the data does not settle into a steady pattern. It continues to evolve. New variations appear. New fluctuations are detected. New questions emerge. This suggests that the region beyond the heliosphere is not static. It is dynamic. It has its own internal processes, its own structures, its own behavior, and that leads to a possibility that is both fascinating and unsettling. What if the solar system is not just sitting inside a stable environment? What if it is moving through a region that is itself complex, layered, and constantly changing? What if the anomalies Voyager is detecting are not isolated events, but part of a larger pattern? A pattern that reflects the structure of the interstellar medium itself? Because if that is true, then Voyager is not just exploring the edge of the solar system. It is revealing the nature of the space beyond it. And that space may be far more intricate than we ever imagined. But here is where the mystery deepens even further, because the anomalies are not random. They repeat, they form patterns, they evolve over time in ways that suggest something more than simple variation, something that might require new explanations, new theories, new ways of thinking about the boundary between our solar system and the galaxy. And that's exactly what scientists began to do. Because when the data no longer fits the model must change. And in this case, the changes would lead to a range of competing ideas, each attempting to explain what Voyager had found, some grounded in known physics, some pushing the limits of current understanding, all trying to answer the same question: what exactly is happening just beyond the edge of our solar system? The moment the data was confirmed, it did not arrive with celebration. It arrived with silence. Not the absence of sound, but the kind of silence that follows when expectations collapse. When something you thought you understood suddenly no longer fits the picture. Because the first real anomaly was not subtle, it was unmistakable. As Voyager 1 crossed beyond the heliosphere, its instruments began detecting plasma waves unlike anything predicted for that region. These were not faint background oscillations. They were clear, measurable signals that appeared suddenly and with surprising strength. According to scientists working with data at NASA, These plasma waves allowed them to calculate the density of the surrounding medium, and when they did, the result forced them to pause. The density was far higher than expected, not just slightly off, significantly different from the models. This alone was enough to challenge assumptions about the interstellar medium near our solar system. For decades, it had been treated as a relatively sparse environment with only a few particles per cubic centimetre. But Voyager's measurements suggested something denser, something more structured. And then came the second shock. The waves did not occur once. They repeated, at intervals, with variations that hinted at movement. These were not random fluctuations. They were events triggered by something travelling through the medium, compressing it and leaving behind a measurable signature. To understand why this mattered, imagine dropping a stone into a still pond. The ripples spread outward, carrying information about the disturbance. If the pond is uniform, the ripples behave predictably. But if the pond has regions of varying depth or density, the ripples change as they move. They speed up, they slow down, they bend, they interact. That is what Voyager was seeing. The plasma waves were like ripples moving through an invisible ocean, revealing the structure of the medium they travelled through. And what they revealed was not uniformity, it was complexity. But the real turning point came when scientists realised what was causing these waves. They were linked to shock waves originating from the sun. Massive eruptions, known as coronal mass ejections, can send disturbances racing outward through the solar system. These shocks travel for months or even years, eventually reaching the outer regions where Voyager resides. When they arrive, they compress the plasma, generating oscillations that Voyager can detect. This was expected. What was not expected was how those shocks behaved once they reached interstellar space. According to studies published in journals like Nature, the strength and structure of the plasma waves suggested that the shocks were moving through regions of varying density. In some cases, the waves were amplified, indicating denser regions. In others, they weakened, suggesting more sparse areas. This implied that the interstellar medium near the heliosphere is not a smooth gradient. It is patchy, layered, possibly filled with small-scale structures that had never been directly observed before. And then there was the timing. The intervals between these plasma wave events did not align perfectly with predictions. Some shocks arrived earlier than expected. Others were delayed. This suggested that the medium itself was influencing the speed and propagation of these disturbances. In other words, space was not just a passive backdrop. It was actively shaping how energy moved through it. This realization marked a shift in perspective, because until this point the interstellar medium had often been treated as a relatively simple environment, thin-cold and mostly uniform. But Voyager's data was revealing something far more dynamic, a medium with a structure, with variation, with properties that could change over relatively short distances. And then came another anomaly, the magnetic field. While the overall direction remained aligned, there were fluctuations in strength and orientation that did not fit neatly into existing models. These variations suggested turbulence, but not the kind of random turbulence expected from a chaotic system. Instead, there appeared to be patterns, subtle but present, regions where the magnetic field behaved differently, as if Voyager was passing through invisible boundaries. This raised a new possibility. What if the interstellar medium is divided into regions, each with its own magnetic characteristics? What if these regions interact with the heliosphere in ways that create the anomalies we are observing? And what if the solar system is currently moving through one of these regions? This idea was not entirely new. Astronomers have long known that the galaxy contains interstellar clouds regions of gas and dust with distinct properties. But these clouds were thought to be relatively large and diffuse, not something that would create rapid variations on the scale Voyager was detecting. Yet the data suggested otherwise. Smaller structures, sharper gradients, a more complex environment than previously assumed. And then perhaps the most intriguing observation of all, the consistency. These anomalies were not isolated incidents. They repeated, they evolved, they followed patterns that suggested an underlying cause. Something influencing the environment in a way that could be tracked over the time. This is what transformed curiosity into urgency, because in science, a single anomaly can often be explained away, but repeated anomalies forming patterns demand a new explanation, and so scientists began to reconsider their models. They revisited assumptions about the heliosphere, They examined new data from missions like IBEX, which had already hinted at unexpected structures in the boundary region, including a mysterious ribbon of energetic particles that did not fit existing theories. They looked at observations from telescopes like the Hubble Space Telescope, searching for clues about the interstellar environment surrounding our solar system. And slowly a picture began to emerge. Not a complete picture, not yet, but enough to suggest that something fundamental had been overlooked. Because the space just beyond our solar system is not empty. It is not uniform. It is not static. It is a dynamic environment shaped by forces we are only beginning to understand. And Voyager, drifting quietly through that environment, is detecting the first signs of that complexity. Signs that something is interacting with the boundary of our solar system. Not dramatically, not in a way that would be visible to the naked eye, but persistently, consistently, in ways that leave measurable traces in the data. And if those traces are real, if they reflect actual structures in interstellar space, then the implications are profound, because it means that the solar system is not isolated. It's embedded in a larger environment that is active, structured, and constantly changing, and that environment is beginning to reveal itself. But the question remains, what exactly is causing these patterns? What forces are shaping the region just beyond the heliosphere? And why do the observations not align with the models we trusted for so long? To answer that, yet scientists turn to competing theories, different explanations, each attempting to make sense of the same data, some grounded in known physics, others pushing the boundaries of what we understand, all trying to explain one simple, unsettling idea: that something outside our solar system is influencing its very edge. At first, the anomalies could be explained away. A fluctuation here, a measurement error there, a temporary disturbance caused by solar activity. Each observation taken on its own had a plausible explanation, nothing that required rewriting the physics of the heliosphere. But then the data kept coming, and more importantly, it began to repeat. Not in identical ways, but in patterns. Subtle, evolving patterns that suggested something more than coincidence. As Voyager 1 continued its journey deeper into interstellar space, scientists noticed that the plasma wave events were not isolated incidents. They appeared in sequences spaced over time, each one carrying information about the environment through which it had travelled. According to NASA, these events could be traced back to solar eruptions that had occurred months or even years earlier. Coronal mass ejections, massive bursts of solar plasma and magnetic fields had launched shockwaves that propagated outward across the solar system. When these shocks reached Voyager, they compressed the surrounding plasma, producing measurable oscillations. That part made sense. Some sense. But what did not make sense was how those oscillations behaved. Some waves arrived stronger than expected, others weaker. Some appeared to stretch over longer periods while others dissipated quickly. And when scientists mapped these variations over time, a pattern began to emerge. The medium was not consistent. It was changing. Imagine sending pulses through a material and measuring how they travel. If the material is uniform, the pulses behave predictably. But if the material has layers, differences in density, or hidden structures, the pulses reveal those features. That is exactly what was happening. Voyager was not just detecting plasma waves. It was mapping an invisible landscape, and that landscape was not smooth. It had regions, boundaries, possibly even currents. One of the most intriguing aspects of this pattern was its persistence. The variations did not fade as Voyager moved farther away from the heliosphere. If anything, they became more pronounced. This suggested that the structures were not confined to the boundary itself. They extended into interstellar space, and that raised a critical question. Were these structures part of the interstellar medium, or were they created by the interaction with the heliosphere? Because if they were intrinsic to interstellar space, then our understanding of the galaxy's local environment was incomplete. But if they were caused by the heliosphere's interaction with that environment, then the boundary itself was far more active than we had imagined. To complicate matters further, the magnetic field data began to show its own patterns. While the overall direction remained aligned, there were fluctuations in strength and orientation that appeared to correlate with the plasma wave events. This hinted at a connection, as if the same underlying structures were influencing both the plasma density and the magnetic field. According to studies in the Astrophysical Journal, Such correlations could indicate regions where magnetic pressure and plasma density are linked, forming structures that can guide the propagation of waves and particles. In simpler terms, space was behaving less like an empty void and more like a fluid with properties that vary from place to place. And then came the most unsettling realization. The patterns were not random. They had a direction. As Voyager moved forward, the variations it detected suggested gradients, gradual changes in density and magnetic properties that implied movement through a structured environment. This was not just turbulence. It was navigation through a landscape that we could not see but could only infer through the behavior of waves and particles. At this point, scientists began to consider a possibility that had once seemed unlikely, that the solar system is moving through a region of interstellar space with distinct characteristics. A region that is different from the one we occupied before, because the sun does not sit still. It travels through the Milky Way, carrying the entire solar system with it. Over millions of years, it passes through different interstellar environments, each with its own density, temperature, and magnetic structure. If Voyager's data was showing consistent patterns, it might mean that we are currently entering such a region. And if that is true, then the changes observed at the heliosphere's boundary are not temporary. They are part of a larger transition. But there was still uncertainty. Because with only one spacecraft, it is difficult to distinguish between local effects and large-scale structures. What if the patterns were caused by localized turbulence? What if Voyager had simply passed through a small irregular region that did not represent the broader environment? These questions could not be answered easily. There were no other probes in interstellar space to provide comparison, no way to map the region in multiple directions, only one path, one stream of data. And yet even with that limitation, the consistency of the patterns made it difficult to dismiss them as random. They persisted over time. They evolved in ways that suggested continuity. They hinted at an underlying structure that extended beyond the immediate vicinity of the heliosphere. And that is what forced scientists to move beyond simple explanations. Because when patterns persist, they demand interpretation. They demand theories. Different ways of explaining the same observations. Some of these theories were grounded in well-established physics. Others required new ideas, new models, new ways of thinking about how the heliosphere interacts with the galaxy. And all of them were trying to answer the same question. What is shaping the environment just beyond our solar system? Because whatever it is, it's not passive. It is not uniform. It's not the quiet, empty space we once imagined. It is something more complex, something with our structure, something that leaves a signature in the data, and perhaps most intriguingly, something that we are only just beginning to detect. This is where the mystery deepens, because once patterns are recognized, the next step is to explain them, to build models that can reproduce the observations, to test those models against new data, to refine our understanding of the forces at work. And in this case, the competing theories would reveal just how much we still do not know, because each theory explained part of the data, but none explained all of it. And that meant one thing. We were missing something fundamental about the boundary between our solar system and the galaxy, something that Voyager had detected, but that we did not yet fully understand. And as scientists began to explore these competing ideas, the possibilities became both fascinating and unsettling, because some of them suggested that the region just beyond our solar system is far more dynamic than we ever imagined, and that whatever is out there is not just surrounding us. It is interacting with us. Once the patterns could no longer be ignored, the focus shifted. It was no longer about whether something unusual was happening. It was about explaining what that something might be. And almost immediately, the scientific community divided into competing interpretations, each grounded in real physics, each supported by pieces of the data, but none capable of explaining everything. The first and most conservative explanation was also the simplest. That the interstellar medium near our solar system is not uniform, but instead filled with small-scale variations in density and magnetic structure. According to this view, Voyager was not detecting anything fundamentally new, just a level of detail that had never been observed directly before. Scientists at institutions like NASA and collaborations with universities such as Caltech suggested that these variations could be caused by turbulence within the local interstellar cloud, a region of space through which our solar system is currently moving. In this model, the plasma waves' magnetic fluctuations and density changes are all natural consequences of a complex dynamic medium, like ripples and currents in an ocean. Nothing mysterious, nothing external acting on the solar system in a deliberate way, just physics operating on scales we are only beginning to measure. But this explanation had limits, because while it could account for variation, it struggled to explain the consistency of the patterns, the repetition, the apparent gradients, the sense that Voyager was moving through regions with distinct boundaries rather than random turbulence. So a second theory emerged, that the solar system is currently entering a new interstellar cloud. Astronomers have long known that the galaxy contains multiple clouds of gas and dust, each with its own properties. Our solar system is believed to reside within a region known as the local interstellar cloud, a relatively low-density area embedded within a larger structure sometimes referred to as the local bubble. But these clouds are not static. They drift, they overlap, they have edges, and according to some researchers, Voyager's data may be capturing the transition between such regions. If that is true, then the changes in plasma density and magnetic behavior are not random. They are markers of a boundary, a transition from one interstellar environment to another. This would explain the gradients observed in the data. It would explain the variation in shockwave behavior. It would even explain the persistence of patterns over time, because Voyager would not be moving through a chaotic medium but through a structured one, a layered environment with distinct regions. But this theory raised its own questions, because if we are entering a new interstellar cloud, then the heliosphere itself should respond. Its shape should change, its size should adjust, its ability to shield the solar system from cosmic radiation might be affected, and yet we have limited data to confirm these larger-scale changes. We are still relying on a single probe, a single trajectory, a single perspective. Which brings us to a third, more complex idea, that the anomalies are not just due to the interstellar medium itself, but to the interaction between the heliosphere and that medium. In this model, the boundary is not just reacting to external conditions, it is actively shaping them. Magnetic reconnection, plasma instabilities and wave interactions could create structures that extend beyond the heliopause, influencing the environment in ways that are not purely external or internal. According to studies published in journals like Science, such interactions can produce regions of enhanced density, magnetic turbulence and wave propagation that would appear as structured variations in Voyager's data. In other words, that the heliosphere might be leaving a kind of imprint on interstellar space, a disturbed region where the influence of the Sun extends farther than we expected, not as a dominant force, but as a subtle shaping presence. This idea blurs the boundary even further, because now the question is not just what is outside the solar system, but how the solar system itself is modifying that environment. And then there was a fourth possibility, one that pushed the limits of current understanding, that the local interstellar medium contains structures we have not yet fully mapped or even theorized. Filaments of plasma, magnetic flux tubes, small-scale density waves. These structures, while consistent with known physics, have not been directly observed in detail at this scale. Voyager's data could be the first evidence of such features. Support for this idea comes in part from observations made by missions like IBEX, which detected a mysterious ribbon of energetic neutral atoms encircling the sky. This ribbon did not fit neatly into existing models and suggested that the interaction between the heliosphere and the interstellar magnetic field is more complex than previously thought. If such large-scale features exist, it is reasonable to suspect that smaller-scale structures might also be present, hidden, invisible, only detectable through indirect measurements, like the plasma waves Voyager is recording. And finally, there is a fifth perspective. Not a separate theory, but a synthesis. That all of these explanations may be partially correct, that the interstellar medium is indeed structured, that the solar system may be entering a new region, that the heliosphere is interacting with that region in complex ways, and that the result is a combination of effects that produce the patterns we observe. This is often how science progresses, not through a single breakthrough, but through the gradual integration of multiple ideas, each one explaining part of the puzzle, together forming a more complete picture. But at this stage, the picture is still incomplete, because there are gaps, observations that do not fit cleanly into any model, variations that remain unexplained. Questions that have no clear answers, and that is what makes this moment so compelling. Because we are not just refining our understanding, we are discovering that our assumptions were incomplete, that the boundary of our solar system is not a simple interface, that the space beyond it is not a uniform void, that the interaction between the Sun and the galaxy is more dynamic than we imagined, and perhaps most importantly, that we are only just beginning to see it, because Voyager is still travelling, still sending data, still revealing new details about a region that until recently was entirely beyond our reach, and with each new measurement the mystery deepens. Because every explanation raises new questions, every theory reveals new uncertainties, and every answer leads to something unexpected, which brings us to the next step. Because if Voyager's data alone was not enough to fully explain what is happening, scientists needed more evidence, more perspectives, more observations from different instruments and missions. And that is when they turn their attention back toward the inner solar system, looking not outward but inward to see if the signs of this mystery could be detected closer to home. If Voyager was the lone observer at the edge, then everything else we had was indirect. But indirect does not mean useless, because sometimes the most revealing clues do not come from where you are looking, but from how different pieces of evidence begin to align. And that's exactly what began to happen. As scientists struggled to interpret the data from Voyager 1, they turned to other missions, other instruments, other ways of observing the invisible boundary surrounding our solar system. They were not looking for confirmation, they were looking for patterns, and slowly those patterns began to appear. One of the most important pieces of evidence came from Ibex. Unlike Voyager, Ibex does not travel to the edge of the solar system. Instead, it orbits Earth and detects energetic neutral atoms, particles that originate from the boundary region and travel inward, carrying information about distant interactions. Think of Ibex as a kind of remote sensor. It cannot go there, but it can read the echoes. And what it found was something unexpected. A ribbon, a narrow band of enhanced particle emissions stretching across the sky, forming a structure that no existing model had predicted. According to NASA, this ribbon is likely related to the interaction between the heliosphere and the interstellar magnetic field. But its exact origin remains uncertain. Why it forms a ribbon instead of a more diffuse pattern is still not fully understood. What matters is that it exists, and it points to something important. The boundary of the heliosphere is not uniform. It has structure, large-scale structure. Now combine that with what Voyager is detecting. Small-scale variations in plasma density, fluctuations in magnetic fields, patterns that suggest movement through a layered environment. Two very different perspectives, two very different methods of observation, and yet both pointing to the same conclusion. The region around our solar system is structured, but the evidence did not stop there. Observations from the Hubble Space Telescope began to add another layer. While Hubble cannot directly observe the heliosphere, it can study the interstellar medium by analysing how light from distant stars is absorbed as it passes through space. These absorption lines reveal the composition, density and motion of interstellar gas. And what Hubble has shown is that the local interstellar medium is not uniform. It contains variations, clouds, regions with different temperatures and densities. This supports the idea that our solar system is moving through a complex environment, not an empty void. And then there is the James Webb Space Telescope. While Webb is primarily focused on distant galaxies and the early universe, its infrared capabilities allow it to study cold gas and dust with unprecedented sensitivity. Observations of similar interstellar regions elsewhere in the galaxy reveal structures that are far more intricate than previously thought. Filaments, clumps, gradients, all existing within what was once assumed to be a relatively simple medium. These observations do not directly measure the space around our solar system, but they provide context. They show that complexity is not the exception, it is the rule. And then there are ground-based observatories and radio telescopes which map the distribution of neutral hydrogen in the galaxy. These maps reveal large-scale structures including bubbles, shells and clouds shaped by past supernovae and stellar winds. Our solar system is located within one such structure, often referred to as the local bubble, a region of lower density created by ancient stellar explosion. But even within this bubble, there are smaller structures, local clouds, boundaries, transition. So when Voyager detects variations, it is not an isolated observation. It's part of a larger pattern that's becoming increasingly clear. The space around us is not uniform. It is layered, structured, dynamic, and that realization brings us closer to a breakthrough. Because when multiple lines of evidence begin to converge, it means we're approaching a more complete understanding, not a final answer, but a model that can explain more of what we are seeing. Scientists began to integrate data from Voyager, Abex, Hubble, and other sources, building simulations that attempted to reproduce the observed patterns. These models incorporated magnetic fields, plasma dynamics, and the motion of the solar system through the galaxy. And what they began to show was both fascinating and unsettling. The heliosphere is not just a passive bubble. It's interacting with its environment in ways that create complex structures. The interstellar medium is not just a background. It is an active participant in shaping the boundary. And the solar system itself is moving through regions that can change the nature of that interaction. This is where the idea of a breakthrough begins to take shape. Not a single discovery, but a shift in perspective. From thinking of space as empty to understanding it as a medium. From seeing the heliosphere as a static shield to recognizing it as a dynamic interface. From assuming uniformity to embracing complexity. And within that complexity lies the answer to the original question. What is waiting outside our solar system? The answer is not a single object, not a hidden planet, not something watching or waiting in the way we might imagine. It is something more subtle, more fundamental, an environment. A structured, dynamic region of interstellar space that interacts with our solar system in ways we're only beginning to understand. But even this realization is not the end of the story, because understanding that something exists is only the first step. The next step is to explain it, to translate complex data into something we can grasp intuitively, to build a model that not only fits the observations but also makes sense of them in a way that can be communicated, tested, and refined. And that is where the breakthrough becomes truly meaningful, because once you can explain something simply, you begin to truly understand it. And in this case, the explanation would require a shift in how we think about space itself, not as empty, but as an ocean through which our solar system is moving, an ocean with currents, layers, and hidden structures. And once you see it that way, everything begins to change. To understand what Voyager is detecting, you have to let go of one idea, the idea that space is empty. Because if you imagine space as nothing as a vacuum with no structure, no motion, no variation, then nothing Voyager is seeing will make sense. But if you imagine space differently, everything begins to align. Imagine an ocean. Not water, but something far thinner, almost invisible, made of particles so sparse that you would not feel them if you passed through. Yet despite that, this ocean has currents, pressure, and structure. It has regions that are slightly denser. Regions where magnetic fields stretch like invisible threads. Regions where disturbances travel like waves carrying energy across vast distances. This is what the interstellar medium is, and our solar system is moving through it. The heliosphere, that a protective bubble created by the sun, is like a vessel drifting through this ocean. It is not isolated. It is not stationary. It is constantly interacting with the medium around it. According to NASA, the solar wind pushes outward, creating pressure that inflates the heliosphere. At the same time, the interstellar medium pushes inward, creating a balance that defines the boundary. But in an ocean, balance does not mean stillness. It means constant adjustment. Currents shift, pressure changes, waves move through the water, and anything traveling through that ocean responds to those changes. This is the key to understanding Voyager's data. The plasma waves it detects are like ripples moving through this invisible ocean. When a shockwave from the sun travels outward, it does not move through empty space. It moves through a medium that can compress, expand, and vary in density. If the medium is uniform, the wave behaves predictably. If the medium has structure, the wave reveals that structure. This is why the plasma waves vary, why their intensity changes, why their timing does not always match predictions. Because they are moving through an ocean with currents and layers. Now think about the magnetic field. In this ocean, magnetic fields are not static lines. They're more like currents within the water guiding the motion of charged particles. The sun's magnetic field extends outward, carried by the solar wind, while the interstellar medium has its own magnetic structure. Where these two systems meet, they do not simply stop. They interact. They twist around each other. They create regions where the field becomes stronger or weaker, where particles are guided in new directions. This is why Voyager's magnetic field measurements show fluctuations, not random ones, structured ones, because the spacecraft is moving through regions where the magnetic properties of this ocean change. And then there is density. In a true vacuum, density would be constant at 0. But in this, ocean density varies. Some regions have slightly more particles, others slightly fewer. These differences may seem insignificant, but over the vast scales of space they matter. They influence how waves propagate, how particles move, how energy is transferred. And this is exactly what Voyager is detecting. Small changes, subtle variations, but consistent enough to reveal a pattern. Now here is where the analogy becomes even more powerful. Imagine that your vessel is not just drifting randomly, it is moving along a path. And as it moves, it passes through different parts of the ocean. Some calm, some more turbulent, some with gentle currents, others with shifting flows that push against the vessel. That is what the solar system is doing. It is not fixed in place. It is traveling through the galaxy, moving through different regions of interstellar space. According to astronomical measurements, the Sun is currently moving through a region known as the local interstellar cloud. But this cloud is not uniform. It has edges, it has gradients, and beyond it there are other regions with different properties. If the solar system is approaching or entering one of these regions, the heliosphere would respond. Its shape would adjust. Its boundary ratio the interaction between the solar wind and the interstellar medium would change, and Voyager sitting at the edge would detect those changes. This is why the data feels so dynamic, because it is capturing a moment in motion, a transition, not a fixed state but a process unfolding over time. And that leads to a crucial realization. The anomalies are not anomalies in the sense of errors. They are signals, clues about the structure of the medium through which we are traveling, clues that the ocean around us is more complex than we thought, and perhaps most importantly clues that we are not in a static environment. We are moving through layers, through regions, through structures that are invisible to us except through their effects. This is why the patterns matter, because they are not random. They are consistent with movement through a structured medium. They suggest gradients, transition, boundaries that are not sharp but gradual. And once you see it this way, the mystery becomes clearer. It's not that something is suddenly appearing outside our solar system. It is that we are moving into something that has always been there, something we are only now able to detect. But this raises an important question. If space is an ocean, and the solar system is moving through it, then what lies ahead? What regions have we not yet encountered? What structures exist beyond the reach of our current instruments? And how might those regions influence the heliosphere, and by extension, everything inside it? Because if the environment around us can change, then the conditions within our solar system are not entirely fixed. They are influenced by where we are in the galaxy, and that realization has consequences, not just for our understanding of space, but for Earth, for life, for the future of exploration. Because the ocean we are drifting through is not empty. It is active, it has currents, it has structure, and we are only just beginning to understand it, which leads to the next step. Because once you accept this analogy, once you see space as a dynamic medium, the implications begin to unfold, and they reach far beyond the edge of the solar system. Once you begin to see space as an ocean, a medium with structure, movement, and variation, a new question naturally emerges. If the solar system is moving through this ocean, then where exactly are we going? Because motion implies direction, and direction implies that the environment ahead may not be the same as the one behind. For a long time, this idea remained mostly theoretical. Astronomers knew that the Sun orbits the center of the Milky Way. They knew that it travels through regions of varying density and composition, but these changes were thought to occur over immense timescales far beyond anything we could observe directly. Voyager changed that, not by showing the entire journey, but by capturing a single moment within it, a moment where the environment appears to be shifting. According to researchers working with data from NASA and collaborating institutions including groups at MIT, the solar system is currently embedded within a region known as the local interstellar cloud. This cloud is part of a larger structure sometimes referred to as the local bubble, a vast cavity of low-density gas believed to have been created by ancient supernova explosions. Within this bubble, smaller clouds exist, each with its own characteristics. The local interstellar cloud is one of them. It is relatively warm compared to other regions with temperatures around several thousand degrees years Kelvin, though still incredibly diffuse. It contains a mix of neutral atoms, ions, and magnetic fields that define the environment just outside our heliosphere. For decades, it was assumed that this cloud was relatively stable, that we were comfortably embedded within it. But newer observations suggest something more dynamic. Data from missions like IBEX indicates that the direction and properties of incoming interstellar particles are not perfectly uniform. There are subtle variations, hints that the flow of material around the heliosphere is changing. At the same time, studies of interstellar absorption lines using instruments like the Hubble Space Telescope suggest that the local interstellar cloud may have a complex structure with gradients in density and composition. In other words, it may not be a single uniform region. It may have edges, boundaries, transitions, and if that is true, then the solar system may be approaching one of those boundaries. This is where the idea of a larger galactic structure becomes important, because the local interstellar cloud is not isolated. It is surrounded by other clouds, each with different properties. Some are denser, some colder, some have stronger magnetic fields. If the solar system moves from one cloud into another, the environment around it changes. And when the environment changes, the heliosphere responds. It may compress, it may expand, its shape may distort. Its ability to shield against cosmic radiation may increase or decrease. This is not speculation without basis. According to studies published in journals like the Astrophysical Journal, models of the heliosphere show that even modest changes in the density of the interstellar medium can significantly alter its size and structure. If the surrounding density increases, the heliosphere could shrink. If the magnetic field strengthens, it could become more compressed and distorted. And if the solar system enters a region with very different properties, the changes could be even more pronounced. This is where Voyager's data becomes particularly intriguing, because the variations it detects in plasma density and magnetic behavior could be early indicators of such a transition. Not a sudden crossing into a new cloud, but the gradual approach. The outer edges. The first hints that the environment ahead is different from the one behind. Imagine sailing through an ocean and beginning to notice subtle changes in the water. The temperature shifts slightly. The currents become more complex. The color changes just enough to suggest that something lies ahead. You have not reached it yet, but you can sense it. That is what Voyager may be detecting. And if that interpretation is correct, then we are witnessing something remarkable. Not just the exploration of interstellar space, but the movement of our entire solar system into a new region of the galaxy, a region that could have different properties, different levels of radiation, different magnetic structures, and those differences could have real consequences, because the heliosphere is not just a boundary, it is a shield. It protects the planets from a significant portion of galactic cosmic rays, high-energy particles that can damage biological tissue, disrupt electronics, and alter atmospheric chemistry. If the heliosphere changes, that protection changes. According to NASA studies, variations in cosmic ray flux have been linked to changes in atmospheric processes on Earth. While the effects are subtle and operate over long timescales, they are real. This means that the solar system position within the galaxy is not just an abstract concept. It has tangible effects. Effects that could influence planetary environments, radiation levels, and even the conditions for life. And yet we are only beginning to understand this connection. Because until Voyager we had no direct measurements of the region beyond the heliosphere, and even now we have only one perspective, one path through a vast and complex environment. But that path is enough to raise questions. Important question. Questions that challenge our assumptions about stability, isolation, and the nature of the space around us. Because if the solar system is moving into a new region, then the changes we are observing are not temporary anomalies. They are part of a larger process, a process that will continue as we move through the galaxy, and that leads to a realization that is both fascinating and humbling. We are not just observers of the universe, we are participants within it, carried along by the motion of our star, drifting through regions we cannot yet fully see, influenced by forces that operate on scales far beyond our everyday experience. And right now, at this moment in time, we may be entering a region that is different from anything we have experienced before. But here is the uncertainty. We do not yet know exactly what that region is. We do not know its full structure. We do not know how it will evolve. And we do not know how it will affect the heliosphere over time. All we have are hints, patterns in data, variations that suggest change, signals that point towards something ahead. And that brings us to the next question. If these changes continue, if the heliosphere responds to this new environment, what does that mean for everything inside it? If the heliosphere changes, everything inside it feels the difference. Not instantly, not in ways you would notice tomorrow or next year, but over time in subtle, measurable shifts that ripple through the solar system. Because the heliosphere is not just a boundary, it is a shield, a vast invisible layer that reduces the intensity of galactic cosmic rays before they reach the inner planets. According to NASA, this shielding effect plays a role in maintaining the radiation environment that Earth and other planets experience. Without it, the solar system would be far more exposed out. Now imagine that shield changing, not disappearing, not failing, but adjusting in response to the environment around it. If the solar system enters a region of higher interstellar density, the external pressure on the heliosphere increases. This could compress the bubble, making it smaller. A smaller heliosphere means less distance for cosmic rays to travel through solar influence before reaching the inner solar system. In simple terms, more high-energy particles could penetrate deeper. If the surrounding magnetic field becomes stronger or more turbulent, it could distort the heliosphere, creating regions where shielding is weaker. Not everywhere, not uniformly, but in localized areas where the boundary is pushed inward or stretched thin. And these changes, while subtle, have consequences. Cosmic rays are not just abstract particles, they carry enormous energy. When they collide with planetary atmospheres, they can trigger cascades of secondary particles influencing chemical reactions in the upper atmosphere. Studies referenced in journals like Nature have explored how cosmic ray flux can affect cloud formation, atmospheric ionization, and long-term climate patterns. The connections are complex and still debated, but the principle is clear. The environment outside the solar system can influence conditions within it, and that includes Earth. For astronauts, the implications are even more immediate. Beyond Earth's magnetic field, exposure to cosmic radiation becomes a serious concern. Missions to the Moon, Mars and beyond must account for this. If the heliosphere's shielding effect changes, the radiation environment for space travel changes with it. Higher radiation levels could increase risks for long-duration missions. It could affect spacecraft electronics. It could influence how we design habitats and protective systems for future exploration. And then there are the outer planets. Planets like Jupiter and Saturn have strong magnetic fields of their own, which provide additional shielding. But smaller bodies like Mars or the moons of the outer solar system are more exposed. Changes in the heliosphere could alter the radiation environment around these worlds, affecting their atmospheres, surfaces, and potential habitability over long timescales. But perhaps the most profound implication is not practical, it is conceptual, because for a long time we have thought of the solar system as a relatively stable environment. Yes, planets move. Yes, the sun goes through cycles. But the broader context, the space around us, was assumed to be constant. Voyager's data challenges that assumption. It suggests that the solar system exists within a changing environment, that the galaxy is not just a distant backdrop, but an active participant in shaping the conditions within our cosmic neighborhood. And this changes how we think about our place in the universe. Because it means that the conditions we experience on Earth are not just determined by our planet and our sun. They're also influenced by where we are in the galaxy, by the regions we pass through, by the structures we encounter. This is not something that changes overnight. These are processes that unfold over thousands, millions of years. But they are real, and they are measurable, and they are happening now. The variations Voyager detects are not just interesting anomalies. They are early indicators of a larger system at work, a system in which the solar system is embedded, a system that is dynamic, structured, and constantly evolving. And this leads to a deeper question. If the environment around us can change, if the heliosphere can respond to those changes, then what limits do we face in understanding it? Because right now, our knowledge is based on limited data. One spacecraft beyond the heliosphere, a handful of missions observing indirectly, models that are constantly being refined. There is still so much we do not know. We do not know the full structure of the interstellar medium around us. We do not know how quickly it changes. We do not know how the heliosphere will respond over long timescales. And we do not know what lies ahead, because the solar system is moving, and wherever it is going, it is carrying us with it. This is where the mystery becomes more than scientific. It becomes philosophical, because it forces us to confront a simple idea, that our environment is not fixed, that our place in the galaxy is not static, that we are part of a journey that began long before humanity existed and will continue long after. And right now, we are only beginning to understand the path we are on. But here is the challenge. Understanding requires data, and data requires exploration. And at this moment, our exploration is limited. Which brings us to the next question. If we want to understand what is truly waiting outside our solar system, how do we go there? How do we observe it? How do we map a region that is billions of kilometers away with only a single probe to guide us? Because the answer to that question will define the next chapter of this story. For all that we have learned, the most honest answer remains the simplest. We do not fully understand what lies just beyond our solar system. We have data, we have patterns, we have models that explain parts of what we see, but there are still gaps, important gaps, and those gaps are where the most compelling questions live. Take the plasma density variations that Voyager 1 continues to detect. We know they are real. We know they are not random. We know they are influenced by shock waves and the structure of the interstellar medium, but we do not know the full geometry of that structure. Are these variations part of large coherent regions that extend across vast distances? Or are they smaller localized features that Voyager happens to be passing through? With only one spacecraft, it's difficult to tell. We are sampling a three-dimensional environment along a single line, and that limits what we can infer. Then there is the magnetic field. We know it does not shift as dramatically as expected at the heliopause. We know it shows fluctuations that suggest interaction and turbulence, but we do not know how these magnetic structures are arranged on larger scales. Are there filaments, layers, regions where the field is stronger or weaker? And how do these regions connect to the broader magnetic structure of the Milky Way? These are not small questions. They are fundamental to understanding how our solar system interacts with the galaxy. And then there is the issue of boundaries. If the interstellar medium contains clouds regions with distinct properties, where exactly are their edges? Are they sharp transitions, gradual gradients? Do they overlap? Do they move? And if the solar system is approaching such a boundary, how long will the transition take? Years, centuries, millennia? We simply do not know, because the timescales involved are vast. Voyager has been traveling for decades, and yet it has only just begun to sample this environment. The changes it detects may represent only a small fraction of much larger transition. And then there is this question of scale. The structures Voyager is detecting appear to have size. They influence the propagation of waves. They affect particle densities. They shape magnetic behavior. But how large are they? Are we talking about regions that span billions of kilometers? Or structures that extend across light years? Without multiple probes, without a way to map these features from different angles, it is extremely difficult to determine their true extent. This is one of the biggest limitations of our current knowledge. We are observing a vast complex system with a single point of measurement. And while that point is incredibly valuable, it cannot provide the full picture. There is also the question of time. The interstellar medium is not static. It evolves. Shock waves from distant supernovae can propagate through it. Magnetic fields can shift. Clouds can move and interact. This means that the environment Voyager is detecting today may not be the same as the one it will encounter tomorrow. And that raises an important point. The patterns we see are snapshots, moments in a dynamic process. They tell us what is happening now, but not necessarily what will happen next. And then there is perhaps the most intriguing unknown of all, the nature of the structures themselves. We can infer their existence, we can model their effects, but we cannot directly observe them in detail. They are invisible, made of particles and fields that do not emit light in ways we can easily detect. We rely on indirect measurements on the behavior of waves and particles to reveal their presence. This is like trying to understand the shape of a landscape by listening to echoes. You can learn a great deal, but there will always be uncertainty. And then there is the broader context, the galaxy itself. We know that the Milky Way contains a vast network of interstellar structures, clouds, bubbles, filaments, all shaped by the life cycles of stars. But we do not know exactly where we are within that network. We have maps, but they are incomplete. We have models, but they are still evolving. And so we are left with a situation that is both exciting and humbling. We have crossed the boundary of our solar system. We have taken the first steps into interstellar space. And yet we are still at the very beginning of understanding what that space is. Because every answer we find leads to new questions. Every pattern reveals deeper complexity. Every model highlights new uncertainties. And that is how science moves forward. Not by eliminating mystery, but by refining it. By turning unknowns into questions, and questions into investigations. But there is a limit to what we can do with the tools we have. Voyager is aging, its power supply is slowly fading. At some point it will fall sunt, and when it does, we will lose our only direct connection to the region beyond the heliosphere. Unless we send something new, something designed specifically to explore this boundary, to map it, to measure it from multiple directions, to provide the data we need to move from speculation to understanding. And that brings us to the future. Because if we want to answer these questions, if we want to know what is truly waiting outside our solar system, we will have to go there. Not once, but many times, with new missions, new instruments, new ways of observing the invisible. Because the mystery is not going away. It is only becoming clearer. And the next step is to meet it head on. If Voyager is the first whisper from the edge, then the future will be a chorus. Because what we have learned so far is only the beginning. The data from Voyager 1 has revealed that the boundary of our solar system is not simple. It is dynamic, structured, and influenced by forces we are only starting to understand. But one spacecraft following a single path can only tell us so much. To truly understand what lies beyond the heliosphere, we need to return. Not with one probe, but with many, and this time with purpose. According to NASA, one of the most ambitious concepts currently under study is the Interstellar Probe mission. Unlike Voyager, which was designed for planetary exploration, this mission would be built specifically to travel beyond the heliosphere and study the interstellar medium directly. Its goal would be clear: to map the boundary, to measure its structure, to observe how it changes over the time, and most importantly to provide multiple data points that allow scientists to build a three-dimensional picture of the region, because that is what we are missing. Perspective. Imagine trying to understand a storm by standing in one place. You can feel the wind, you can see the clouds, but you cannot see the full structure. You cannot know where it begins or where it ends. Now imagine observing that same storm from multiple locations, from above, from within, from different angles. Suddenly patterns emerge, structures become visible. The system begins to make sense. That is what future missions aim to do. The interstellar probe, still in the planning stages, would travel much faster than Voyager, potentially reaching distances of hundreds of astronomical units within a few decades. It would carry advanced instruments capable of measuring plasma, magnetic fields, dust, and energetic particles with far greater precision. It would not just detect anomalies, it would map them. At the same time, other missions and observatories will continue to provide indirect observations. Instruments like IBEX and its successor, the Interstellar Mapping and Acceleration Probe, will refine our understanding of the heliosphere's structure by detecting energetic neutral atoms from different regions. These missions act like scanners, building a global picture of the boundary from afar. And then there are telescopes. The James Webb Space Telescope will continue to study interstellar environments across the galaxy, revealing how gas and dust behave under different conditions. While it cannot directly observe the heliosphere, it provides context showing us what similar regions look like elsewhere. Ground-based observatories and radio telescopes will map the distribution of interstellar gas tracing the larger structures through which our solar system is moving. Together, these efforts will begin to fill in the gaps. But there is another challenge: distance. Voyager is currently more than 24 billion kilometers from Earth. Signals take over 22 hours to travel one way. Any new mission will face the same challenge, operating at the limits of communication power and time. This means that exploration of the interstellar boundary is not just a scientific challenge, it is an engineering one. We need spacecraft that can operate for decades, power systems that can last for generations, communication methods that can transmit data across vast distances with minimal loss, and navigation systems that can guide a probe through regions we have never mapped. This is not easy, but it is not impossible. Because we have already done it once. Voyager proved that it can be done, and now with modern technology we can do it better, more precisely, more deliberately, more comprehensively. But here is the deeper question. Why does it matter? Why invest decades, resources and effort into studying a boundary that lies so far beyond our immediate reach? The answer is simple: because it is the boundary of our cosmic home. Understanding it means understanding the environment in which the solar system exists. It means understanding how the galaxy influences us, how cosmic radiation reaches us, how the conditions for life are shaped not just by our planet, but by our position in the Milky Way. It also means preparing for the future, because as humanity looks beyond Earth, as we consider missions to other planets, other stars, the environment beyond the heliosphere becomes increasingly relevant. It is not just a distant frontier, it is the next step, and the more we understand it, the better prepared we will be to explore it. But even with new missions, new data, new models, there will always be limits, because the galaxy is vast, the interstellar medium's complex, and our ability to observe it will always be constrained by distance and technology, which means that some questions may remain unanswered, at least for now, and that is part of the journey. Because exploration is not just about finding answers, it's about asking better questions, refining our understanding, pushing the boundaries of what we know. And right now, the boundary we're pushing is the edge of our solar system, a place that until recently was entirely beyond our reach. Now it is within our grasp, not fully understood, not fully mapped, but no longer invisible. And as we prepare to explore it further, one thing becomes clear. Whatever is waiting outside our solar system, we are going to find it. Not all at once, not easily, but inevitably, because that is what we do. We explore, we observe, we learn, and with each new mission, each new measurement, each new piece of data, the mystery becomes a little less distant, a little more defined, a little closer to understanding. But even as we look forward, there is one final thought that remains. Because beyond all the science, all the data, all the exploration, there is a deeper question, one that goes beyond what we can measure, beyond what we can observe, a question about what it means to exist within this vast dynamic universe. If you could step outside the solar system, if you could drift beyond the last reach of the sun's influence and look back, what would you see? Not planets, not orbits, not the familiar structure we map in textbooks. You would see a small, fragile bubble, a thin envelope of energy and particles glowing faintly against the vast darkness of interstellar space. Inside it, everything we know exists. Every world, every ocean, every moment of human history. And outside it, something far larger. Something we are only beginning to understand. For most of human history, we imagined ourselves at the center of everything. Then we learned we orbit the sun. Then we learned the sun is just one star among hundreds of billions in the Milky Way. And now with data from Voyager 1 and decades of research from organizations like NASA, we are beginning to understand something even more subtle. That even our solar system is not self-contained. It is not isolated. It's part of a larger environment that is dynamic, structured, and constantly changing. The heliosphere, once thought of as a stable boundary, is now understood as a living interface. It responds to the galaxy. It shifts. It adapts. It interacts with the interstellar medium in ways that ripple inward, influencing the conditions within. And beyond it, the space we once imagined as empty is revealing itself to be something else entirely. An ocean, a medium filled with particles, magnetic fields, and structures that we cannot see directly but can infer through their effects. Voyager has given us our first glimpse of that ocean, Not a complete map, not a full understanding, but a set of signals, patterns, clues that point toward a reality more complex than we expected. And perhaps that's the most important lesson. Because every time we have expanded our view of the universe, we have discovered that it's not simpler than we thought. It is more complex, more interconnected, more dynamic. The edge of our solar system is not a quiet boundary. It is a place of interaction, a region where the influence of our star meets the influence of the galaxy, where forces from vastly different scales converge, where the familiar transitions into the unknown. And that transition is not just happening somewhere far away. It is happening around us, right now. As the solar system moves through the Milky Way, it carries us with it through regions we cannot yet fully see, through structures we are only beginning to detect. We are passengers on a journey that spans light years, a journey through an environment that is not fixed but evolving. And the data from Voyager suggests that this journey is not smooth. It is not uniform. It is shaped by the structure of the galaxy itself, which means that the conditions we experience, the radiation that reaches us, the environment that surrounds our planetary system, all of it is influenced by where we are in that journey. This is not something we feel in our daily lives. It's not something that changes from one generation to the next. But it is real, and over long timescales it matters. It matters for understanding the history of our planet. It matters for predicting the future of space exploration. And it matters for answering a deeper question. What does it mean to exist in a universe that is not static but constantly in motion? Because the more we learn, the clearer it becomes that there is no fixed position, no permanent state. Everything is moving. Everything is interacting. Everything is part of a larger system, and we are part of it. The signals from Voyager are not just scientific data. They are messages. Not messages in the sense of intention, but in the sense of information. They tell us that the boundary we thought we understood is more complex, that the space beyond it is more active, that our solar system is embedded in a dynamic environment that we are only beginning to explore. And perhaps most importantly, they remind us that there is still so much we do not know. Because even now, after decades of exploration, after sending probes to the outer planets and beyond, after building telescopes that can see to the edge of the observable universe, we are still uncovering surprises just beyond our own cosmic doorstep. That is both humbling and inspiring. It means that discovery is not something that only happens in distant galaxies. It is happening here, at the edge of our own solar system, in a region we once thought was simple, now revealed to be anything but. And as Voyager continues its journey slowly fading, as its power diminishes, it carries with it one final role. To be our witness, to send back the last piece of data from a region we have only just begun to understand. And when it finally falls silent, drifting forever in the interstellar medium, its journey will not end. Because what it has revealed will continue to shape our understanding. It will guide future missions, inspire new questions, drive us to explore further. Because the mystery it uncovered is not going away. It is expanding, and somewhere beyond the edge of the heliosphere, beyond the reach of the sun's influence, beyond the limits of what we can currently observe, there is still more to discover. Not something waiting in the way we might imagine, but something existing, something structured, something that is part of the same universe we inhabit. And as we move through that universe carried by our star, surrounded by this invisible ocean, the question is no longer whether there is something out there. We know there is. The question is, how much of it have we yet to see?